dive into the fascinating world of machine learning where support vector machine or SVM reigns supreme in tackling classification and regression problems. As a powerful supervised learning algorithm, SVM is tasked with the creation of a decision boundary, known as a hyperplane, with the purpose of separating data points into distinct classes. The power lies in its unique selection of support vectors, which are extreme cases that aid in the formation of this hyperplane. Now, imagine the versatility of SVM as it weaves its magic in a myriad of applications. From distinguishing faces in a crowd with face detection, to categorizing images with image classification, and even organizing text through text categorization, SVM is truly an integral part of the machine learning toolkit. It comes in two flavors, linear and nonlinear, each with its own special way of separating classes of data. Indeed, SVM stands as a testament to the advancements in machine learning, revolutionizing the way we handle data. So, what makes SVM so powerful? Let's break it down. At its core, the support vector machine, or SVM, is a supervised learning algorithm. This means it learns from data that has been labeled or classified already. It's often used for classification and regression problems, but let's focus on classification for now. Imagine you have a bunch of data points scattered across a plane. These data points belong to different groups or classes. The goal of SVM is to find a line that best separates these classes. But this isn't just any line, it's a special kind of line known as a hyperplane. A hyperplane is like a boundary line, but in multiple dimensions. In a two-dimensional space, the hyperplane is a line. In a three-dimensional space, it's a plane. And in anything beyond that, well, it's a hyperplane. This hyperplane is what SVM uses to separate the data points into their respective classes. Now the question is, how does SVM find this hyperplane? This is where support vectors come into play. Support vectors are data points that are closest to the hyperplane and influence its position and orientation. These are extreme or critical cases that help SVM draw the best hyperplane. But the world isn't always linear, and neither is our data. Sometimes a straight line just can't do the job. This is where the magic of SVM really shines. It can add additional dimensions to handle nonlinear data. This is called nonlinear SVM. By mapping the data to a higher dimensional space, SVM can find a hyperplane that separates the classes, even if they seemed inseparable in the original space. By manipulating dimensions, SVM has the ability to handle both linear and nonlinear data, making it a versatile tool in machine learning. Now you might be wondering, how can we implement SVM in our own projects? Well, support vector machine, or SVM, can be implemented in Python using a key tool from the S.V.M library, known as the SVC class. The SVC class is where the magic happens, making it possible to incorporate SVM into your machine learning toolbox. Now, what makes SVM so adaptable is the ability to fine-tune its performance. This is achieved by adjusting certain parameters. Let's delve a bit into these parameters. Firstly, we have the regularization factor. This helps to prevent overfitting by controlling the trade-off between achieving a low error on the training data and minimizing the norm of the weights. Next is gamma, an essential parameter for nonlinear SVMs. It defines how far the influence of a single training example reaches, with low values meaning far and high values meaning close. Lastly, we have the kernel. The kernel function allows us to add more dimensions to our data, making it possible to handle non-linearly separable data. A range of kernel functions are available, from linear to radial basis function, offering flexibility based on your data's needs. With Python and Sklearn, SVM becomes accessible and easy to implement, opening a world of possibilities for data analysis. It's time to wrap up our brief journey into the realm of SVM. We've delved into the heart of this popular supervised learning algorithm, uncovering its purpose in classification and regression problems. By creating a decision boundary or hyperplane, SVM masterfully separates data points into distinct classes. The algorithm's strength lies in its support vectors, the extreme cases that help carve out this hyperplane. We've also explored the two types of SVM, linear and nonlinear. The former uses a straight line to distinguish classes, while the latter adds extra dimensions to separate nonlinear data. Our journey took us to the practical side of SVM, demonstrating its implementation in Python with the SVC class from the Sklearn.svm library. We've seen how the performance of the SVM model can be tweaked by adjusting parameters such as the regularization factor, gamma, and kernel. With its power and versatility, SVM undoubtedly holds a vital place in the field of machine learning, a tool that can transform raw data into insightful information.